Hello world. In the previous video, we installed Lean4 and created a project. This is where we left off last time. So we were just about to prove the statement that appending two strings and taking the last character is just equal to taking the last character of the second string. This doesn't actually hold true universally because there are SNTs that makes this false. Maybe you can see it right away, but I'll proceed from here and then come back to add the missing precondition when we run into a dead end. Okay, let's get started. Okay, I'll assume that you know what induction is, and then I'll be inducting on S. Okay, S could be an empty string. That's one case. Okay, for this case, just reflection. By definition, what we just see in the hover panel is this goal. And if you know Lean4, you will see immediately that this is just the appending of strings is the appending of the data character list. And appending an empty list to another list is by definition just the second list. And then so they take on the exact same form. T.back. This will reduce to T and then T.back, which takes on the exact same form as the right hand side of the equality, and so this can be closed by reflexivity. Okay, this is going to be a little tricky. Let's also try to destruct the T. Okay, I don't care about this in the first case. Second case, I can call it BS. So by definition, this is what we're doing. Oh, let's open the namespace string so that we can get back directly. Of course, this won't hold so trivially. We'll have to construct this proof one step at a time. Okay, the first thing we'll have to do is to unfold the definition of back. So what exactly is back? Okay, let me shorten certain things. Give A, give the appending AS and BS and alias CS. Okay, give you this. By definition, it is exactly this. What's missing? Parentheses. Definition of the ending position. UTF-8 bytes. Okay, since I'm unfolding things, I assume that later on the proof is just reflexivity. Okay, now we're trying to unfold this by definition. Okay, reduces to a call on the data list, character list. In this case, we're in the cons arm, so it should reduce to n post cs plus c. Okay. Give it a short name. Let's unfold the definition for previous. Should look like this. Okay, how do we proceed from here? We see that there are two if statements. Oh, sorry, correction. If expressions. These are actually expressions that we evaluate to the left side or the right side, depending on whether the condition is true or false. So somehow we will have to unfold these if expressions. So at this point, can we even know that if 0 is q or p is less than I prime? Let's start here. Under what condition can p be less than I prime? So CS is a character list, and then it is converted to a string, and then we're taking the ending position of that string, which is the sum of the UTF-8 character size for all the characters inside this character list. Suppose CS is empty, then the ending position would be 0. In that case, P would be equal to I prime, and this will hold, so this will give us 0. And in any other case where CS is not empty, then CS will contain at least one character, leading to the ending position of the string to be greater than 0. So in that case, P will never be less than I prime, and then the right-hand side will be taken. So it seems like we have to argue by cases. So let's try to do that. Argue by cases on. CS. So either CS is empty or CS contains can be broken down. It contains at least one character. Okay, no matter what we're trying to do, let's tidy certain things up. In this case, we would want to, first of all, want to show that P is actually end post. CS is 0. Okay, reflexivity doesn't give us a why. Why is that? The ending position of an empty string should just give you 0. So by definition, it should be 0. Then why is it not reducing to 0? Okay, now it is. But what I want is CS. Okay, the reason is that matching does not make CS and the empty string and the empty list definitionally equivalent. There's something going on behind the scene that makes them only propositionally equivalent. So this is the syntax to get the equality for this branch to be taken. Okay, so now if we try to substitute this equality into reflexivity, then we get the proof. And we can keep reducing. So next thing is to show that P is C. Oh, it's alright. I don't really have to reduce it that far. I just only have to show that. I can just also show that. Same thing. P gives by definition. By definition. No, this one close, so trivial. There's some replacement we have to do. We have this. Great. So it's still a simple substitution. I'll close this up. Oh no, it won't work like this. Make it a one-liner. You need the type spelled out for the substitution to know how to do. Okay. So in this case, we know that Q would be 0. They are equal. So then the natural knows their positions. Definitionally, they are the same thing. Okay, now we have Q equals 0. Say if Q is 0. Okay. We are now in this position, meaning that we're trying to prove this and this to be equal. So that's a calculation. The left hand side will be just this. What's the matter? Oh, okay, I don't really care about the right hand side. It should be C. It hinges on 0 being Q, which we have proved, but we need to take its symmetry. Okay, what about this? What can we get out of BS? Okay, make an observation. We know that CS is an empty list, and CS is AS appended with BS. So intuitively, there is no way for AS and BS to not be both empty lists as well. I believe there's an existing theorem that we can just use. Okay, let's call it. We want to show that given that CS is HBS. Let's do this. Let's see if there's a shorter theorem that we can use. Okay, this looks good. So in this case, we have CS being AS appended with BS. And then we will get the implication that both of them are empty list, and we want the right hand side. Okay, mix put E into it, take the right hand side. Okay, now I have this. So let's reason backwards. Should be this after substitution. Substitute. Okay. So what exactly is this? What is the back of an empty string? What does it say in the comment? It returns the last character in S. So in the case of S being empty, return default character. So by default character, so by definition, it should be this. Okay, we're reasoning backwards. Default, which reduces to capital letter A, capital A, capital A. Okay, so now how can we actually show that C will always be A? What exactly is C? C is the first string being decomposed to its first character followed by the rest of the string. How can you how can you be sure that the first character of S is actually capital A? You can't, right? You see the problem. The counterexample. Okay, lowercase a. This is clearly a counterexample. Man, this is false. What you should be proving is not equal. Okay, in Lean4, the not operator is actually just something implies false. So implication is a function type. So we should be taking its, I'll spell everything out. What this is exactly this, and then having the return value being false. This is what not means. Okay, some proposition, not something, is that something implies false. Okay, how do we show false from this? Or let's try not doing this whole. Let's calculate all the way. So what exactly is this? By definition, it should reduce to little a.back. It should reduce to just character little a. Let's reason backwards. This reduces to default character. As we can recall, this is actually uppercase A. The way to close this is by calling no fun. It's saying that there is no function with this holding. Okay, this is something we'll have to elaborate in the future. But let's just say that when you see certain literals or constructors, I mean base cases that are clearly not true by definition, the no fun will be able to close it. Okay, so we have uncovered a counterexample to this. So what should we add to the precondition for this for us to proceed? We would never be able to complete this because it is false. There is a case for it to be false. Not every C would be uppercase letter A. So we'll have to somehow avoid getting into this situation. So let's reason backwards. The only way for us to get here, I mean, assuming that all of these reasonings are correct, and in Lean4 we can have full confidence that it is true because the compiler checks it for us. The only reason is that we have CS being empty. So we have to rule this out. Take a look at CS. What CS is? CS is AS appended with BS. And for whatever AS, if we wish that CS is never empty, then we must require BS to not be empty. Otherwise, if AS, in one case, in which that AS is empty, then we'll have the appending of two empty lists leading to an empty list. So it is absolutely required that T is not empty. Oh man. Okay, given this condition, we should be able to tell Lean4 to never have matched this case. So how are we going to do this? Let's implicitly have this fact. So suppose we have this in the declaration, and at this very point, we would be able to remove this whole section. See? Very interesting. Okay, we will also try to explain this in the future, just not now. Just assume that for certain very explicit cases, I mean simple cases like this, CS not being one of its constructor, which is in this case nil, not being empty, and having it in the context prior to this match, then Lean4 will somehow be able to utilize this fact and then rule out the possibility of having me to declare this string, this part of the match. Take a look again. Suppose I comment this out, right? You'll see a warning saying that it's missing one case. But somehow this will be able to allow the compiler to exclude that case, the empty case. Okay, great. Let's first close this. How are we going to do this? Okay, since we have opened the string, we should be able to use the extensionality. Okay, so it assumes that it's list of characters, if them being equal, then S1, and then the strings will be equal. What we want is false. This is actually okay. What we have here is just this. What did I get wrong? In this case, T, yes. God, what am I missing? Why isn't extensionality working? Oh, no, what I have is this. What I have is this. Sorry. Okay, this requires further reasoning. So I believe it is already built in. Not nil. Okay, let me see. Ah, I did this up. Great. Now we can reason into this. Then it zeros Q. Can Q now be zero? Is there any way for this to be possible? No, because as we reasoned before, given that CS is not empty, then CS contains at least one character, and so the ending position would never be zero. It would be in fact greater than zero. Hence, something greater than zero adding to C would never be less than or equal to zero adding to C. Okay, so this is false, man. Gotta prove it. Okay, let's try to proceed in the main argument first. This should give us the latter part. Okay, let me just leave it like this. What I want to even unfold this, or should I just leave it like this for a while? Okay, let me try to unfold Q. Let's see what Q is. This is Q. So somehow, let me name this HQ. Q in this. Q is not zero because this is false, meaning that it will take the second range. Meaning that, oh, okay. The reason that we can get to this is because of a prior effect stating that this is false. Okay, so we'll have to prove this and then derive HQ0 from this. Great. Even more things to consider. P less than I prime. We know that for this is false, meaning that it will take this. Ah, so this is not that trivial. How can we be sure that this is not zero as well? Okay, we need a further cleanup. Anyway, for the time being, let's just keep on going if neg HQ. What is I prime plus C? God. We'll be able to replace Q with this, and then how will we be able to proceed? Suppose I don't need the final structure of CS, at least not here. Hey, what the? Oh, I see. Okay, it's propositional equality creeping in. Let's just keep it like this. How am I going to proceed? Okay, let's for the time being see what we have here. Can we further reduce this? CSI prime. What is I prime? This is I prime. What is P? How can this be reduced? Let's take a look at this definition. Let's see. Given a string and a position, prev will give you the previous position in that string. The previous position. What does it mean? Okay, let's look at the example. So we have a string ABC. Its ending position would be the position immediately after C, and then applying, and then taking the previous position of this last position. Okay, should give you the position right before C, so that when you try to get that position, the character of that position inside the same string, it should give you the character C. Okay. So if you take the previous position 3 times from the ending position, it should give you, okay, the position for this character. Okay, it kind of makes sense. So how does this auxiliary definition achieve that? So it breaks it down into 0 and P position, starting from 0 to P. 0 to P. So given an empty list of characters, it will always give you the byte index of P minus 1. What about this? Inductively, if the character list is not empty, then it will append advance I with number of bytes for C to represent the C. And then see if P is less than that. Okay, I see. So what it does is that it accumulates all the characters from the beginning of the character list to the point where until it is no greater than P. Okay. Okay, so it's just accumulating the length of character, byte length of characters. Oh, until you are no less than P. And then that very previous position I. Okay, it should be the position. Okay, I see. So given this definition, we might attempt to prove this auxiliary theorem. Okay, so suppose you have list character figure of positions. You might want to show that this is previous position plus R. Okay, so intuitively we might want to attempt this. And so if this is true, if this is true, then we will know that this reduces to okay. So recall the special case where the first position is 0. It is actually just priv by definition. The shorter form would be this. Okay, let's give it another name. Q is actually R. Let's see. Okay, with this we can now have this equality. Okay, so again, I primes this. Okay. Then we might want to prove another auxiliary theorem similar to this, but with regards to this function. Okay. What would you guess? Going back to the definition. Getting a character at a certain position. Getting the character at position P of string S means to call into the auxiliary definition with 0 being the second argument, I being 0, I being 0. Okay, see, so it increments this second argument I by the size of the character and keeps on incrementing it until the point that I reaches P, and it will give you the destructed character. Okay. So in this case, if you advance both positions, then it should still work. It should give you the same thing. Let's name it auxiliary 1. Let's have a guess. By advancing both positions. It should stay the same. Okay. So with the second auxiliary definition, you should be able to conclude 0 and R. And recall that having the second position and the first position, which is the second argument to UTF-8 to get aux, it's actually the special case where it reduces to just get. Definition of get. So you're trying to get this position of the string CS. Okay, let me just write it as CS. And what is R? Wow, this is R. Making this the definition of back. What we have here is just this. Okay. And since at the beginning we're performing a destruction of S into a smaller list of string, so we can actually recurse on this, making this an inductive proof by calling it into the smaller case where we have the base case here. Let's name this. Something's missing. Oh, it should be an explicit argument. What we have here is BS not being empty. BS not being empty. Don't we have a proof of it somewhere? exactly the case of H. That is just H. Great. How many stories do we have here? Okay, we'll have to close these things. Let's start with this. Remember that these are just mere guesses, but I mean, inspired by the definition. So to proceed with proofs, we still have to rely on our intuition to look at certain things, to follow in a certain direction. That's why we guessed at these auxiliary theorems. Okay, so guessing is a crucial part of this, an educational guess. And then we close them up and to see if we are missing anything. Oh, these are slightly more complicated, so I'll leave it here. Let's try to close these things first. P being less than, not greater than I. Okay, but remember that CS is not empty. Making this positive, so it would always be greater than I prime. So suffice we have P greater than I prime. Not empty or great. Yeah, this of G, not LE of GT. P greater than definition. This is what we want to show. This is what we want to show. Okay. The same thing as taking its content, comparing its content. So position is composed by a natural number. Point one would just reduce to this. You can also write this. They're the same thing. I use one for short. Okay. The reason why I do this is to make an argument, arguing in to reduce this to an argument in the natural numbers instead of positions, so that I can sidestep all the extensionality for a position. Okay, what does this give me? PS plus C. Okay, wait a moment, let me think. By definition, n poses CS. It should be adding C. Oh, we're already there. No, no, no. CS plus C. How is this not? Oh, okay. Breaking this up. Plus X. All I want to show is that this is greater than 0. And then by adding two more things, hitting the same thing to both sides of the inequality should give you the same inequality. So, suffice to prove this. What do I have here? How am I going to achieve this? So, I have. Okay, there as a fact, we have this. We have the UTF-8 size of the character X would always be positive. And then if something is positive, then adding something to its left should retain its positivity. There is a theorem for this. Um, Adding something to its left. Great, this should work. C, in this case, C is this first part. Then why is it not? Wait a second. Oh, no. What I'm doing is proving this. Suffice, so I have to construct this inequality from this. Okay, I get it. Natural number, so I have this first part covered. And then they're adding both sides by C, so add LT, add right, adding C to the right. This, and let it deduce. Okay, C for me. Great, this closed. Do we want to shorten this? Alright, doesn't matter, just leave it like this. Okay, what about this? For this very case, okay, well, what exactly is Q? What's the point of, oh, okay. I want to show that. Huh. Okay, it's used right here. So this is Q. Now where is this used? What the, okay. Down below. Not required by any of the preceding part. 0 not equal to Q. Q being this. R plus C. C is okay. Okay, so the reasoning follows from this. Same kind of reasoning. Okay, what I want to do is let's make this easier to prove by having 0 on the right hand side. Similarity calc. Oh no, take some detour. Given that Q is R plus C, and we know that C is greater than 0, then this whole thing will be greater than 0, hence Q being greater than 0. Q not being 0. Alright, same thing. What? Okay. Extensionality. Or is it other? Hmm. What seems to be the problem? It is not zero, it's false. Let's break it down. Oh, not extensionality, the other way around. Eh? Isn't this just substitution? Isn't this just substitution? Great. Man, stuff's not easy, man. Okay, we're right here. We are right here. Q being greater than 0. Okay. Nice fact. Let's see by this. Greater than 0. Using the same argument. This part. Add to the left, given C is positive. Great. So this is closed. Not exactly trivial. Great. Now comes the two auxiliary theorems. And let's start with the second one. Reason by induction. Okay, let's use a special syntax for this. Okay, for the case that it's empty. For the case that it is not. Wouldn't I just give you the default by reflexivity? Okay, let's reduce the left instead. Auxiliary P plus R equals Q plus then C plus P plus R plus Q plus. What am I doing wrong? Oh, missing ranks. Don't worry. The non-trivial part. What require further the same single boolean in CLs. P plus C and Q. Okay, great. How do we know these two things are the same? Okay, first of all, we can see that these two conditions are equivalent. And then on the true branch, they return the same thing. And on the false branch, they return something very familiar, which is just recursing back into the same auxiliary theorem, but with a smaller CS. Okay. But for this to work, you would need C and R switching places. So we need to somehow still replace this. Okay, let's do it. There is a theorem for this. For the if expression having all of the branches and the conditions being congruent, and then one can replace the other. See, the first thing is to prove that these two things are the same. God, not exactly trivial is this. Okay, IFF propositional extensionality. Okay. Okay, what are we trying to show? Calc. Ah, okay, we have theorem for this. Nothing wrong, right? And see, this is the theorem for commuting the right the two right terms for a three-term addition. Here, commuting these two, which is exactly the case we have here. Still wrong. What is it? Why is it? Okay, I know why. These are additions for. Maybe Pose has it. Let me see. Add character commute. Man, but R is not a character. Man, okay. Two ways to do this. First, recall that when we are using auxiliary two, we're actually only advancing by another character. So R can be replaced by a character, and then the type will be correct for add char equal char right commute. Okay, let's do this. First, try this. Let me try this first. Okay, let me make this a what is it called? A point in time. Okay, let's do the stage it, okay, so that we can return to it later. Okay, we're about to do big changes, so we stage it right now. Here, making this a character. All right. Okay, all the rest should work. This is one way to do it. Let me revert it. But actually, the reasoning still hold for a more general case where R is any position, not necessarily just one character. So the only problem is that add right com. It requires the thing being commuted to be natural numbers. Still manageable, still manageable. Just make them natural numbers. Okay, so now this still follows, but with a stronger, but with the theorem being stronger. Although it's a overkill for this case, but it's good to have anyway. I just keep it this way. And then later on, what we're going to P plus C. Okay, so by definition, let's write it in a more suggestive form. This should also work, yes. Because it knows, it can now identify the natural numbers from here. So later on, when it's trying to do the substitution, when it's plugging in the implicit arguments for this theorem, it would actually plug in p plus 1, r plus 1, and c point p.1, r.1, and c point UTF-8 size. And then it will know to deduce the same thing from here and then realize that what I was just replacing, I mean, these things having the second two terms commuted and then constructed into a position is actually just this by definition. So there's some definitional magic happening behind the scenes here. Okay, anyway, the suggested form is for us to see that, okay, in the very first place that we had to convert this into this form is to apply it again, but recursively for a smaller CS. Great, closed. Oh, what about this? Man, it should be this hard. Okay, okay. This direction is a lot easier. It's just substitutions. Okay, 1H. Now this part. I mean, this is just the cancellation rule for natural numbers, but we are stuck with position. There is some form of extensionality that has to be introduced. Say it suffices to prove this equals Q to imply P.1 equals Q.1. Let's see. Suffices extensionality. Oh, no. We're ahead of ourselves. It should be like this. And then No, what now? Introduce. God, why is this so hard? Introducing this into H. And then suffices to prove from something. Say I have this, then I have cancellation rule. Cancel on the right. Cancellation on the right with given this we want this extensionality IFF in this direction. Oh man, the last piece of the puzzle. Man, how long has it been? Let's try the same kind of argument. Just slightly too long. Let's break this line. Okay. Same kind of argument by cases. And then eventually recurs back to auxiliary 1, making this an inductive proof. Oh, what do we have here? What we have here? P.back index. So disregarding the second case, the first case would be, well, recall that CS is empty here. Q plus R. Okay. Equality of positions. Let's first reduce this with extensionality, and this should give us how am I to close this? So Q dot 1 and R dot 1 being natural numbers minus 4, does it actually equals to? Okay, it's kind of false. Okay, this minus is only defined for natural numbers, so see, it saturates at 0, meaning that if Q dot 1 is 0, and then minusing 1 won't give you minus 1 as an integer. It will just stay 0. So there is a counterexample to this. Man, counterexample. 0 plus 1 minus 1 is not 0 minus 1 plus 1. Well, really isn't. By definition, they are not, because this is 1 by definition. We calculate. This is 1 minus 1. Okay, just note that the reduction I'm doing here must hold definitionally as I delete it, as I'm doing a reduction. Otherwise, it will give me a word. For instance, if I write 2 is definitionally not equal to this. Okay, so let's do the reduction and make sure that they are actually definitionally the same. This gives you 0. By saturation, it's 0. It is 0, and then plus and 1 gives you 1. So by definition, 0 is not 1. Okay, see? Problem here. Having seen this problem, seems like we require something more. For this to hold, Q must be positive. God, the detail is overwhelming. Okay. Assuming Q greater than 0. Okay, let's assume that Q is greater than 0. Q is position. Can I do a destruction here? Let me attempt this. Okay, stage the changes as I'm about to do something that I might want to revert later. What? God. Oh, I see. I'm missing something here. You need to show that the end position is greater than 0. Let's come back to this later. For Q to be greater than 0, then we must. Okay, let's try this. Will this work? Imagine Q and R. Let's see if this can just match. Oh, it works. So great. Okay, let me just delete this. Absolutely amazing. Okay, you can make this a one-liner. Let me tell you a trick. You can close this with a tactic. The simplification tactic. Oh, awesome. Let's keep it like this. Great. Okay, now the inductive case. Right. Let's check the definition. This should be definitionally equivalent to no, 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 no. Q plus R. P plus R. Yes. Okay. Typed something wrong. Oh, this is okay. Reasoning from bottom up. It should be a lot shorter. Something plus R. And then wanting it to be definitionally equal. Definitionally equal to the unfolding, which is cube, q less than or equal to p plus c, then p else cs p plus c and q. Okay. We call ITE congruent. We will be doing a similar thing here because these two things are equivalent. The conditions are equivalent. Okay, what about these? You see that we are just moving plus r out of the whole if expression. Why? When originally we have plus r inside both arms. Wait a second. Having it inside both arms would require that this part be okay. Let's do it step by step. First step we want to achieve is this. We want to show that this whole thing reduces to this plus r, which we can see is just the inductive case. We recurse back into the same auxiliary theorem, but using a smaller CS. And since PQ are all, I mean, universally quantified, so they can be anything. And as long as the same requirement that R being positive still holds, Q being positive still holds, then we have the theorem. So for this part, this is it. And then move plus R also out of it. Okay, let's do IT congruent here. Same thing. We'll have to use a propositional equality extensionality for R. Okay, let's call this. No need to give it a name. Reducing to this. Followed and the tricky part. Not exactly tricky, it's just recursive. Reaching this. So let's give it a. This is a rather general statement. Okay, so from my experience, I've never seen what I want that is already defined in the standard library. Nope. Okay, what I want is this kind of congruence. Have body congruence. Yes, something like this. Something having the body being equal, but having a function applied to both sides. But inside both branches of an if expression. Man, it's getting too big. Okay, give it a name here. It should be named independently outside, but for the time being, let's just stick with this. What I'm trying to attempt is this. So given a function, and oh, we have to check on the definition of IT. How is it defined? It requires C to be the condition to be decided. And then T, okay. Same requirements. HT, okay, I can make this implicit. Proposition, making it decidable. Give you T. Okay, let's match on this. It's true. Suppose F. This is what we want here. What seems to be the problem? Okay, make this implicit. I don't want it. Man. Plus R. Okay, great. Given that H is true. Okay. If pose, it should close this. Similarly, if neg. Man, I have such patience. What's the matter here? Recursing into it. Oh, the addition, man, the addition. Same trick, man. What's wrong? Why is it not reducing this time? Reduce, man. What's the difference? Why don't you reduce? Okay, let's try to be explicit. Oh man, dumb as hell. Should be changed. The order. Okay. Q plus recurse. Oh, great. Two more sorries to go. I'm so sorry, man. Okay. Less than or equal to having. Oh, this case is easy. Not exactly that easy. It's just okay. Here's the trick. This statement, where is it used? Here. These are definitionally equal. Okay. No need to pass through extensionality. My God. What we want here is adding R1 on the right would require that these two commute. Okay. Suffice that I prove this being commuted. Okay. Sorry, this first. This would be easier. This is just an existing theorem. Okay. We have this, something less than, and then adding the same thing to the right of both sides. Net LE, let's see, IFF. Add, is there an add? Okay, we have to do it in both directions. Okay, in this direction, from left to right. This is cancellation. We add cancel, cancel. Add and we add. Adding to the right. This would be the other side around. Just y. Oh man. This comes first. Flip it. Not working. Okay, let's do it explicitly. What about this side? Why don't I see my cancellation rule, man? for less than and equal to. I should be using a searching tool, man. Oh, great. Why is it named this way? Man, this is what I'm looking for. This is what I'm looking for. Great. Finally. And this is net.add add right. Will it just close it? Isn't this simple? Should be there, so. Suffices this. Great. Great. Oh man. One more, sorry. See, one more. The ending position being positive. Ending position being positive. CSS. Great, we know how to do this. XX. And now you're adding something positive. And I should have extracted this into a separate theorem, so I don't have to repeat this again and again. Come on. Great. Already have it? Man. Oh, I'm reusing this. Oh man. Oh, okay. We have completed it, but I would like to do a slight modification. Okay, I should be have H prime. Man, not even seeing it. Here. H prime. This one-liner, man. One-liner. What? Nothing wrong, just no need for this. Ah, feels so good. Okay, shorten this. I don't see them again. See if I can just show it. Show. Great. Looking good. Only used once, right? Okay. This is now code golden. This seriously reduces readability, but since I'm just recording a video, I can do it. Record is there. Tidying up the proof. Making it a lot shorter, man. H prime used twice. Okay. Okay. Man, I don't want to go through this again. Anyway, we have the proof now. Stage it. Oh, dear proof. How many lines are there? Line 9. Started with line 9. Looks a bit too long. It should be shorter if one has a better proof strategy. But anyway, this is a raw demonstration of how you perform proofs in term mode in the Lean4. Okay, albeit this looking rather trivial and innocent, it actually takes quite some effort to prove it. And throughout this whole process, we see that we often leave out critical preconditions as we do all the time in programming. So this is why Lean4 can provide a higher confidence in programming while I'm promoting this thing. It actually closes up all the loose ends in the program. This kind of thing should only be done once. I mean, even better, having this done in a computer science course at college. Yet we don't have this kind of offering. But with enough training, we should be able to do this kind of thing on the job and make this practical. Okay, despite I'm doing a proof, the whole goal is not to do mathematics, but programming instead. So, okay, see you next time. Next time, come up with easier things to do. But this is a first demonstration of all the nitty-gritties of Lean4 proving and everything that most of the things that it provides out of the box is demonstrated here. Although many things require further elaboration, but that's for next time.